If you think machines are mysterious, you're right, but not in the way most people imagine. Every day, you feed a silent classroom. Every search, every click, every selfie uploaded becomes a tiny lesson. Behind the scenes, thousands of algorithms are quietly learning from the patterns of your life. Yet, here's the twist. These systems aren't thinking. They're following invisible rules written by math, mimicking our choices to predict what comes next. It sounds intelligent, it feels human, but what's really happening is closer to translation, a conversion of human behavior into statistics. From your phone's photo enhancer to the chatbot answering your questions, every piece of modern AI is powered by a handful of learning styles that have evolved over decades. To understand how machines learn, you need to see how they were taught, because every algorithm carries a philosophy about how knowledge should be built. The two ways machines learn. At the core of machine learning lie two main paths, supervised and unsupervised learning. Think of them as two philosophies of intelligence. Supervised learning is like raising a child with flashcards. You show it examples and answers. This is a cat, this is a dog. It practices until it can guess correctly on new images. Unsupervised learning, however, is the child with no teacher staring at a pile of photos and trying to find patterns on its own. Most of the systems shaping your world, from Netflix recommendations to spam filters, belong to the supervised family. They work because someone once labeled the data, emails marked as spam or not spam, homes priced in dollars, images tagged as banana or apple. Machines use these labeled examples to learn the hidden connections between inputs and outcomes. But when labels don't exist, unsupervised learning steps in, finding clusters, discovering structure, and exposing relationships we didn't even know were there. The predictors. Supervised learning splits further into two realms, regression and classification. Regression predicts numbers, prices, temperatures, probabilities. Classification predicts categories, spam or not, cat or dog, healthy or sick. Both rely on the same principle. The past can guide the future. When a regression algorithm looks at a city's housing data, it doesn't know what a house is. It simply notices patterns. Bigger homes cost more, certain zip codes are expensive, older buildings may be cheaper. It draws a mathematical relationship between all these variables. Classification works the same way, but replaces numbers with decisions. For example, your email app learns that messages with the word lottery and 10 links are suspicious. It's pattern recognition, pure and simple. The beauty of these systems lies in their humility. They don't think, they observe. They don't reason, they measure. And somehow, that's enough to make them powerful. The early thinkers. Linear regression was humanity's first attempt to make machines see order in chaos. Picture a scatter of points on a graph, each one a story, each one noisy. Linear regression draws a line through them all, trying to minimize the total error. The line itself is simple, but what it represents is revolutionary. Prediction through pattern. Then came logistic regression, a twist on the same concept, but for decisions instead of numbers. Imagine trying to predict whether an email is spam. Instead of drawing a straight line, logistic regression draws a soft curve, one that says, if this email has these words, there's an 80% chance it's spam. It doesn't say yes or no outright, it speaks in probabilities. These two early thinkers became the skeleton of modern AI. Every neural network, every complex algorithm still echoes their logic, mapping relationships, minimizing error, learning from mistakes, the neighbors and the boundaries. The next idea was even more human. What if machines learned by proximity? Enter k-nearest neighbors, or KNN. It's one of the simplest algorithms, no math equations, no training phases. It just remembers data. When you feed it something new, it looks around and asks, who are your closest neighbors? If most of them belong to the spam class, it predicts that yours is spam too. It's like social intuition, guessing someone's interests by the company they keep. Yet this simplicity hides danger. Too few neighbors, and the model memorizes. Overfitting to noise? Too many, and it becomes blind to detail. The sweet spot between both is what gives KNN its charm. And then there's support vector machines, the mathematicians of the machine world. Instead of asking who you resemble, SVMs draw the sharpest boundary between different groups. Picture plotting cats and elephants by weight and height. The SVM draws a line that separates them with the widest possible margin, so when a new animal appears, it's easier to decide which side it belongs to. With something called a kernel trick, SVMs can even bend space, discovering shapes and relationships humans can't visualize. The intuitive thinkers. Probabilities soon entered the picture with naive Bayes, an algorithm built on conditional reasoning. Imagine you're an email filter again. You've seen thousands of spam messages and know that words like free, winner, and click here appear frequently. Naive Bayes uses this knowledge to estimate the odds of a new message being spam. It assumes each word acts independently, which isn't true, but the simplicity makes it fast and surprisingly accurate. Then came decision trees, arguably the most human of all algorithms. They learn by asking questions. Is the patient's blood pressure high? Yes. Is cholesterol above 200? Yes. High risk. It's reasoning through yes/no questions, exactly how doctors, teachers, and judges make decisions. But like people, trees can overcomplicate things, memorizing every detail instead of general truths. That's where ensembles were born. Instead of relying on one decision tree, engineers began combining many, a concept called bagging. The most famous ensemble, Random Forests, creates hundreds of trees, each trained on different data subsets. They vote on the final answer, reducing bias and noise. Boosting takes it further, training models in sequence where each one corrects the mistakes of the last. It's like a relay race of refinement, producing results that often outperform single models. If you're starting to see how these invisible systems quietly shape everything from your Netflix queue to hiring algorithms, take a quick second to like this video and subscribe. It helps more people understand how machines think, not just fear them. And I'll keep breaking down AI topics like this every week. After decades of trial and error, one idea stood out. What if we let the machine design its own features? Instead of manually describing the rules for cats and dogs, what if the system learned those features automatically? That question gave birth to neural networks. Think of a neural network as a layered web of neurons, small units that each make simple judgments, like detecting edges in an image. The first layer might see lines, the next sees shapes, and deeper layers combine them into concepts, like faces or numbers. It's not magic, it's abstraction. Each layer transforms data into something slightly more meaningful. When you add many layers, you get deep learning, where the system builds complex representations. Like understanding the difference between a smiling face and a frown without being told what emotions are. This is how machines started to see, hear, and write. But make no mistake, they don't understand beauty or meaning. They simply remix mathematical relationships until the result aligns with what humans call correct. The explorers. Now imagine you remove the teacher. No labels, no categories, just raw data. How does a machine make sense of that? That's the world of unsupervised learning. It's like dropping someone into a new city without a map and asking them to find neighborhoods by observing who hangs out where. The most famous explorer here is k-means clustering. It starts by guessing where the centers of groups might be, assigns nearby points to each, then moves the centers closer to the data. It repeats this until everything stabilizes. The result? Natural clusters appear. Customer segments, behavior groups, even unseen categories in genetic data. Other methods like hierarchical clustering or DB scan add flexibility, finding clusters of any shape even when they overlap. These systems don't predict, they reveal, showing us patterns we might never have noticed ourselves. The simplifiers. While most algorithms chase complexity, a few are designed for restraint. Dimensionality reduction, led by techniques like principal component analysis, PCA, tries to simplify reality without losing its essence. Imagine you have hundreds of features describing an image: color, brightness, shape, texture. PCA finds which features truly matter and discards the rest. It's like compressing a high-resolution movie into a single meaningful frame. The goal isn't just efficiency, it's understanding. Machines use dimensionality reduction to filter noise, improve speed, and uncover the hidden structure of data. This is how AI learns to focus, because intelligence, at its core, is selective attention. The grand connection. At first glance, these algorithms seem different. Lines, trees, layers, clusters, but step back and you'll see they're all solving the same riddle. How can a machine learn from experience? Linear regression finds relationships. KNN learns by proximity. Random forests trust the crowd. Neural networks invent patterns. Clustering finds order in chaos. Each one is a different dialect of the same language, the language of pattern recognition. And every modern AI system, from image generators to stock forecasters, is just an orchestra of these older ideas, scaled to unimaginable size. The irony is poetic. We call it artificial intelligence, but what it really reflects is human thought, compressed, repeated, and accelerated. When a chatbot speaks fluently, it's not consciousness, it's prediction. When a model detects a tumor, it's not compassion, it's probability. What feels like intelligence is really an echo of us, the human in the loop. So where does that leave us? Machines have learned to simulate understanding, but they still rely on the values we embed. They can optimize profit, accuracy, or speed, but they can't choose kindness, fairness, or meaning. That's not their role, that's ours. Every algorithm mirrors its creator. If we feed it bias, it amplifies discrimination. If we teach it empathy through better data, it amplifies fairness. The reflection is neutral, but the mirror isn't. The future of machine learning isn't about creating sentient robots. It's about teaching better lessons. Because ultimately, AI doesn't replace the human mind, it scales it. It doesn't erase creativity, it multiplies it. The true challenge is not whether machines can think, but whether humans can stay thoughtful while teaching them. So next time a machine predicts what you'll buy, watch, or believe, pause and ask yourself, whose patterns is it really learning from? Because in the end, the secret language of machines isn't written in code, it's written in us.